And we should be recording right now. All right, so today I'm going to start out with our electronics training. Day one, lecture one. We really have to talk about the basics, so we're really not going to talk about electronics so much today as we're going to talk about energy in general. Okay, so it is an electronics course, but energy forms the base of the pyramid for everything we do. Everything we do in mechatronics involves working with energy. Whether it's electrical energy, pneumatics, hydraulics, nuclear energy, solar energy, stored energy, which is where we're headed. All of that is the pyramid, because what we end up doing is, good morning.
Good morning.
We have a pyramid, and on the top of that pyramid is everything we do. So energy is at the bottom. So if we don't understand how that works, we're going to be missing some of that pyramid. Not a good base, no pyramid. So let's start off, and you kind of pointed to this when you said something a moment ago, two types of energy, two generic types of energy.
Potential and kinetic.
What is it?
Potential and kinetic.
Potential and kinetic.
Ball at the top of the hill and the ball going down the hill.
Okay, yep, potential and kinetic. What do they mean? What do those two things mean? They're pretty much common English words, so.
Potential is stored energy.
Like battery.
Like a battery or a ball sitting at the top of the hill or
compressed spring.
or yeah, compressed spring or stretched out bungee.
Yeah, lefties.
And kinetic is energy in action.
So here are some words that potential energy can relate to in our field. Stored energy, that could be gravity, could be pressure, could be voltage, or if it's a motor or something that's turning, the pressure that a motor exerts, even if it's not turning, is called torque. Okay, so, and then there's really one more, which is force. That's linear. Torque is rotary.
Yeah, so force is like with a lever or something.
What's that?
Force would be like with a lever.
Force is more, no, lever is rotational. It goes in a circle. Force is
Like a
pushing
hydraulic,
something. Okay, so if I have a 1,000-pound car,
I wasn't thinking of lever as like on the pivot. I was thinking of like the push of the lever.
yeah, would definitely have to be in a straight line. So pushing a car, if you have a 1,000-pound car, you need 1,000 pounds of force.
Like piston.
Right, piston moves straight, correct. All of these do, or I should say, none of these actually involve motion. Do they?
Nope.
Nope.
They're all static.
Kinetic is energy and motion.
Okay, what's the opposite of static? Static means still.
Yes.
If it's not still, it's moving. And what do we call that? Something that changes.
Dynamic.
Ah, yes.
Dynamic.
That's the word.
Right? There's actually a course that some people take at college called Statics and Dynamics, which involves mechanical energy. Okay, and we don't spend that much time to get into statics and dynamics, but we do talk about mechanical items and forces in our mechanics class, which could be called statics and dynamics, but it would be a misnomer because this is much more calculus, math related, than mechanics is. This goes into the science and behind it all, which we really don't need to know because we're not engineers. Okay, so kinetic involves motion or change. Velocity, RPM, cubic feet per minute when air is moving. We're talking about motion now. Okay. So far, so good, right?
I remember these from 8th grade science.
What's that?
I remember these ones from 8th grade.
Yeah, this is just standard background stuff.
Yep.
But most of what we do involves converting
Potential to kinetic.
from potential to kinetic energy. Okay, we take electricity out of the wall, which is potential energy. There's electrons in there that just dying to get out. They want to get from one side of this to the other. That's what they want to do. There's two slots over there, like this, and this is full of electrons, and this has none. And they really want to get across that gap. So when we plug something in to our outlet, it does some sort of energy conversion. Okay? Anytime we run something off of electricity, it does some sort of electronics or energy conversion where it's converting from potential to kinetic. Okay? Any questions on what's on the board right now? Because I'm going to erase it.
Not create nor destroy energy. Change forms.
Have you heard that before?
And
Yeah, it's pretty common.
Or destroyed, you can just change forms.
And it can change forms and it can do a lot of different things, but it cannot be created or destroyed. It just cannot happen. So that opens up an interesting thought process because what that means is that we can approach energy like we approach a checkbook. We can balance. We can look at how much energy we've put into a system and look at how much kinetic energy we get out, and they should be the same. In fact, they have to be the same. If I have a light bulb and I plug it in, and that light bulb uses 100 watts worth of energy or electricity, then it has to be putting out 100 watts of energy. Whatever it consumes, it must put out. That's the law.
But, wait,
There's no buts about it.
The types of energy may be split.
So,
like you say, so is that factoring in for, say, mechanical frictions and shit and stuff?
everything.
Because that's the whole basis on the reason they can't make a perpetual motion device is because you can't just put in the same amount and get out the same amount, or get out more because of, frictions and
Correct.
stuff like that.
Correct. So if you're putting in 100 watts and you have 0.000001 watt worth of friction, you do not have a potential motion machine.
Yeah.
It may take 50 years for it to stop, but it's still guaranteed to stop,
Yeah.
right? You just don't know when. So let's look at two examples of this. First one, Light bulb.
It's a good light.
Second one. Okay, you know what those are, right? Stove burner, you've seen them, they're a little, about this big around. What's the difference between those two devices?
The types of energy
You know,
that they
one's made to
produce.
create light, but produces heat as a byproduct. One's made to create heat, but produces light as a byproduct.
Okay, but are they basically the same thing?
Yes.
A coil of wire hooked up between positive and negative,
Yes.
right? This one puts out 90 watts of heat, or light, I'm sorry, this would be a light bulb, so it'd be 90 watts of light and 10 watts of heat. This one puts out 90 watts of heat and 10 watts of light. Okay? Now, you only notice that when it's on all the way, correct?
For the most part, yeah.
For the most part. But remember, this is our infrared and this is our ultraviolet. This is our range of vision. Colors of the rainbow. Everything above it is things like X-rays. Everything below it is things like radio waves. So this is what we can see. This is the filter of our eyes. It only lets in this row or list of frequencies. So when we turn on a burner like this at low intensity, it starts to build infrared, but as you continue to turn it up, it bleeds over into the visible light spectrum, and at that point then you can start to see red, and as you turn it up a little higher it starts to get yellowish, orangish as it bleeds more energy into that system. But at any time, the total amount of energy coming out when you add these up in your energy budget has to equal what's coming in. Okay? Does that make sense? So what does this actually do? Both of these devices are in an electrical circuit that looks like this. 120 volts out of the wall, and will represent our light bulb or burner as a squiggly line, which is a resistor. We'll talk more about that later. A resistor limits the speed of energy conversion. Okay? And I'm going to explain what that means in a real down-to-earth way, and I mean that literally. Two guys, one here and one here, and this guy has a square on his back. They both jump out of an airplane. This guy releases his parachute. He looks like this. This guy
Splat.
looks like this. What's happening in
That
this?
parachute is resisting the current of the flow of the air, slowing down the surface
It's
momentum.
creating more resistance, acting as a resistor, slowing his fall. Whereas the other guy, well, he's got all that kinetic energy of terminal velocity.
126 miles an hour. Which is real fast to hit the ground at. Well, it's not the fall that killed him. It's the
Oh,
wind.
yeah, it's just that sudden stop.
Yeah.
It's, you know what it is? It's the conversion from kinetic energy
Potential.
to potential energy, right? Here, that conversion time
It's drawn out.
is maybe more than 1 minute. Anytime we convert energy from one form to another very quickly, we have a problem. It could be an explosion. If we have an explosion, you're setting off a whole bunch of TNT, which is loaded with potential energy. You just need something to release it, and poof. Because it happens so quickly, it's catastrophic. But if you take that same dynamite or whatever and lay it out in a powder on the ground and light it, it'll go it'll fizzle, right? So the speed of conversion is what's important, which we have to worry about with things like turning motors on and off. If we turn motors on and off too quickly, it causes problems with the motors and wastes energy. Okay, consider this. Let's put up another analogy here. Car brakes. What are car brakes used for?
Stopping the car.
Converting energy from dynamic to potential.
Either use friction to slow the kinetic energy as you move the vehicle and convert it into potential.
They're there to correct your inability to regulate or predict fuel requirements. You only use your brakes when you gave it too much gas. Or
When you
because
come
you
to a
can't
complete
predict that somebody's going to cut in front of you and you're going to have to slam on your brakes.
stop. When you need to come to a complete stop.
Or you need to come to a complete stop. But even so, eventually you will come to a complete stop, no matter what.
No,
Why not?
because cars idle in motion.
And eventually they run out of gas.
I mean, yeah, if you run out of.
Eventually
Yeah.
it will come to a complete stop.
Yeah.
Agree with me on that because eventually it will.
Yeah, in that aspect, I'm thinking like just, in a short distance kind of.
But we have to think about energy not just in human terms, but in milliseconds and millennia, right? All that, you put a solar sail out there in space, it's going to take millennia for it to get enough energy to be able to approach 1/10 of the speed of light. So we can't look at it in human terms. And part of the reason for that is because all of this crap ultimately is controlled by computers, which are much faster than our brains are. So what seems like a very short time to us is an eternity to a computer. So we have to keep that in mind. But our car brakes are there. Every time we use our brakes, what happens? You are turning gasoline into heat because your brakes get hot. The extra gas that you used to increase your velocity above that which was required, whether you knew about it or not, it doesn't matter, is going to be the same amount of heat that comes out of the brakes. Whatever you put too much in is going to come out when you try to fix the situation and convert speed to heat, because heat doesn't run into people. Cars do, but if you convert that speed into heat, it just dissipates into the atmosphere and you save yourself an accident, right? So look at energy that way. Another way to look at it is, what happens when you cook something at your house? It raises the temperature of your house, which does what? turns on the air conditioner, right?
Oh, you guys have one of those? You lucky.
Well, if you have one, turns on your air conditioner, and also
Opens the windows.
it makes your refrigerator work harder because it's warmer in the house. So the refrigerator then has a cooling system, but remember, if you're cooling one place, you got to be heating up somewhere else because you don't destroy heat, you just move it from one place to another. So when you're moving heat from inside the refrigerator to outside the refrigerator, yeah, you're getting cold stuff, but now you've increased the heat in your house. And now your air conditioner's gonna have to come on to take up that energy, right? And move that energy from in the house outside where it belongs. Okay, so we can move energy around, we can convert it from one form to another, but we have to be careful at how fast we do that conversion. And that's a lot of what we worry about in our industry, is how fast that conversion happens, how smoothly it happens, at what rate does it happen, and does it happen in a straight line where you have X versus Y? Does Y change linearly with X or does it not? Those are things that we have to concern ourselves with. All right, so in your courses here, you're going to be taking 3 courses that basically involve energy. You're going to be taking electronics, you're going to be taking fluids, and I don't mean you're going to be drinking them, and you're going to be taking mechanics. In electronics, we call potential. Anybody know what we call potential electronics? Begins with a V.
Voltage?
What do we call kinetic in electronics? Anyone know? You probably do.
Electricity?
No.
Oh, that would be.
Current. Current, yeah.
Study of current events. Fluids, potential.
Pressure,
And kinetic.
flow.
And in mechanics, pressure is
Torque.
force
Oh, yeah.
or torque.
Yeah, I can say it's word.
And we'll put an arrow here and we'll put an arrow there. And what about kinetic?
Motion or velocity,
And
rotation, RPMs.
RPM.
Horsepower.
Okay, we're going to finish up our discussion by making believe we're going to buy a pressure washer. Two pressure washers. One is 4 gallons per minute at 3,000 psi.
So take the skin right off.
And this one is 3 gallons per minute at 5,000 psi. Which one do I buy? One's got less gallons per minute but more psi. How do I figure that out?
It's because it's probably using the finer spray tail.
Well, this is what the pump puts out.
Yeah.
These are numbers that are produced under, I'm sure some manufacturers all get together and say, this is how we're gonna rate our pressure washers. Okay, but one thing I want to mention here is that the amount of power is equal to the potential energy times kinetic.
So you would wanna go with the,
The second one.
yeah, the second one, because you multiply 4 and 3, that's 12. 3 and 5, that's 15.
So 4 gallons per minute times 3,000 PSI is 12,000.
That's,
It's not 12,000, it's unitless. It really doesn't have any units. 3 times 5,000 is 15,000. So this one then would be
More powerful.
the most powerful.
Also means it's gonna be the most power hungry.
That depends. That all depends on how much loss there is,
Yeah.
right? Because this thing's job is to pump water. Its job isn't to make heat,
Yeah.
right? So if this one gets a lot hotter than this one does, then you're gonna have that to deal with. Might cost you more to run. So, you know, those are different considerations. There's also price, there's also reliability, there's also Yelp reviews, there's all kinds of things that go into deciding which one we want. And does somebody know what time it is? How are we doing?
9:32.
Good, we're in good shape. Okay, so just because it's the most powerful does not mean it's the best. Because best,
Most powerful for 2 jobs and then brakes and then.
best is dependent on the person, right? What's best for you may not be best for someone else. We have to work in terms of highest value. We don't use terms like best. We don't use terms like that because it really depends on the situation and the scenario.
Best is an opinion.
Right, best is an opinion, but the data is a fact.
Yeah.
So we can always go with that, and if you need to find that information, then yeah, you might have to do some legwork. You might have to, for example, find out what model motor these use, or engine, or however they run, and
What company?
look up that engine and find out how efficient that engine is under what circumstances. So I mean, you could do that research if you wanted to. If you were a company, if you were U-Haul and you were buying 50,000 pressure washers to distribute all among your entire company, then yes, you might do that kind of work.
So
But if
say
you're
they
buying
want
something to
gas
clean
powered-
your sidewalk or clean out the guts of a 55-gallon drum or whatever, you're not generally going to worry about all that. You're going to go with
Gas
reliability.
powered, but the 5,000 PSI has got an air cooled engine and the 3,000 has got a fluid cooled engine.
Yeah, you know, or maybe this one weighs 300 pounds and you got a guy that's going to take it out on the truck, but this one only weighs 180 pounds. There's more to, just the point is there's always more to the game. Whether it's a business or in a factory, there's always more to the game than just the numbers. So you have to kind of keep that in mind. Right? Does that make sense?
Makes dollars.
And hopefully it saves some. So I kind of like to limit the amount of math that we do as much as possible to simple arithmetic, because in most cases, that's really all you need. This is an electrical or electronic circuit. It doesn't matter at this point which one. DC voltage. Resistor. Let's give this a value of 1 volt. That means there is like one platoon of electrons that are trying to get from negative to positive. Okay, they can't go this way because this is divided up basically like something in the wall, is they're not connected inside. So the electrons want to flow out and into the plus side. Nature likes a balance. Okay?
I thought it was the other way around.
What's that?
I thought it was the other way around.
What's that? That it goes this way?
Yeah, from
Yeah,
positive
well,
to
you know, we need to talk about that a little bit.
Electrons are the negative negative particle of a atom. Positrons are the positive particle, and neutrons are the neutral one.
Okay.
So, yeah. Which always confused me. So why do they call, like, when you work in car stuff, the positive is hot and the negative is ground? Does it?
I'm going to explain that. You ready?
Yeah.
All right. See if I can get this on the camera. I got a jar. It's got stuff in it. Okay? So watch what happens. What did I just do?
Empty the jar into the cup.
What did I just do?
Poured the contents into the cup.
But that's what everybody says. But nobody talks about the air that went into this. I completely filled this with air. Yes, I dumped this into here, but whatever I dump into here, because we cannot destroy matter or anything else like that, has to be replaced by something else. What would that be?
The air that was displaced by whatever is in the jar.
The air. The air flowed in this direction. The junk flowed in this direction. Okay? Which one of these two things do we use to power up, say, an air tool? Air? So while the air is much more important to us than the junk in the cup, the junk in the cup is what we see. We don't see the air coming out. We see the junk going into the bottle, but yet it's the air that's important to us in terms of moving energy around. Nothing is powered by plastic chips. Many things are powered by air. So it's the quantity that we don't see that's important. But, and, the same amount of air is flowing in as plastic is flowing out. Does that make sense? So when I look at this situation, we could kind of say that electrons are flowing out, but then something else has to be flowing in. And we can just simply call those gaps. All right, if I have five x's and I move one x forward, I have a gap. When I move the next x forward, the gap moves backwards, like cars waiting to make a stop, moving forward. So for every action, there's an equal and opposite reaction. We keep drawing these little trinkets from our past, little word combinations that we've all heard before. And now we come to realize that those are laws that we can live by. They're actually laws that make life easier because, as I said, we can balance all of this stuff like balancing a checkbook. Everything will be accounted for. Okay, so in this circuit, we have two things we can look at. We can look at the flow of electrons. They go from minus to plus. And we can look at the flow of gaps, which flow from plus to minus. And because of conservation, those numbers will always be the same. So what I'm telling you is it really doesn't matter which one you pick. All right, some textbooks, this isn't one of them, but one of the other textbooks that they use in biomed actually comes in two separate editions. One has the electron flow, and the other one has conventional flow, which follows the gaps. It was easier for scientists back in the early days to see the gaps than it was to see the actual electrons. And there was an assumption made, just like a water tower, that the flow must go from the higher potential to the lower potential, right? But remember, like a water tower, every time a gallon of water goes out of that water tower, what has to happen? A gallon of air has to go in, right? So which one do you measure? You measure the one that you can see. It was easier to measure the current by measuring the gaps than measuring the electrons.
Okay, now that all makes sense.
Right? Does that make sense now? Yeah.
Yeah.
There's just two different ways. So you pick which one makes sense to you. I'm actually more of a conventional guy. I like thinking about motion from high pressure plus to low pressure minus. But every time I think about that, all I have to do is reverse my arrows. So the only difference between the two textbooks is the direction of the arrows. Current direction. All right, so we're good. We're all good with that idea. So we can pick either one. I'm going to go ahead and pick conventional from plus to minus because it's easier for me and it doesn't matter in the real world as long as you understand that the numbers are the same but the direction is different, right? Think about it this way. Steve is 2 feet taller than Bob, right? So is it saying anything different to say that Bob is 2 feet shorter than Steve?
Not
Same
even a
thing.
little bit.
Not even a little bit, exactly. So perspective, and when we talk about polarities, we can understand that we think about things as negative and positive, but when we talk about negative voltages and things like that, there's really no such thing. It's a difference in potential, but if it's backwards, we refer to it as negative. It's just a difference in polarity, right? Same as saying Steve is 2 feet taller than Bob, plus 2. Bob is minus 2 compared to Steve. You're saying the same thing, but it depends on, you have to have a reference. In our world of electronics, reference is ground. Okay? You have to have a reference to measure anything. Otherwise, you got a guy, a one-armed guy saying, hey, I caught a fish this big. How good is that going to do? You need to have a reference, right? So ground, which is 0 volts, is our reference. And that generally refers to planet Earth, which is the source of all electrons. And we use them just like water. We get them, we use them, and we send them back. And in that trip from one place to another, coming out of something like this, we can use them to get things done. All right, I don't know why they don't do this, but when you look at a circuit, plus minus, let's replace that resistor with a turnstile. Electrons are going to go this way. Gaps are going to go that way. So as the electrons flow in this direction, they go through the turnstile, and this thing is going to turn. You just made a motor. Okay? People going into a subway station, coming out of a subway station. Guess what? It's a motor. You're using flow, linear flow, in a single straight line, or both directions, depending, to generate rotation. It's no different. We do it all the time. And as the people walk up against the bar and grab onto the railing or whatever, what are they creating? Heat. They're creating friction, which means that some of the Wheaties that they ate that morning are going to go into heating up the metal of that turnstile, and the rest of the heat, the Wheaties are going to be putting into turning it. So you will have some friction, right? It all goes back to what you had for breakfast, doesn't it? That's what gives you your energy. And as you use your energy throughout the day, you're debiting from that caloric income. Right? You see how all that fits together? Does it make sense? The whole energy thing? That's really what I want to get through today, is the idea of how we use this energy, how we can regulate how fast it transfers, and what a basic electrical circuit looks like. A basic electrical circuit has to have one, an energy source. Two, a conversion device. And three, a complete path from plus to minus. Those are the three things that we must have in order to have an actual functional electrical circuit.